Thank you, Michael, for inviting. Can you hear me? Is it loud enough? Okay, so thank you for inviting me to speak here. So I'm going to talk about some results that we had concerning IC3. This is a joint work with Yotam Feldman. This is actually everything that I'm going to talk about is part of his PhD thesis. And also most of the slides are stolen and adapted from his. So yeah, thanks to Yotam. So Yotam Feldman, Neil Immerman, Muli Sagiv, and James Wilcox. And what we wanted to do in this work is basically understand SAT-based invariant inference. In recent years, there have been a lot of approaches for invariant inference based on SAT. And so this is the partial list. And we want to understand why do they work so well? Why do they fail when they do? How can we make them better? And specifically, we were very interested in understanding IC3 PDR. And our goal in this work, and what I'm going to talk about here, was really to shed some light on why IC3 works so well. So let me just start with some context about the problem that we are addressing, that IC3 is addressing. So the problem that we are trying to solve is verifying safety of transition systems. Verifying safety means to show that no bad state is reachable. And let's just look at a simple example to illustrate. So we have a transition system which consists of a set of initial state. For example, here we have a vector of n bits, and the initial state is just that all of them are 0. Then we have a transition relation describing how the steps of the system. So for example, here the transitions just increment this bit vector by basically by 2. So just incrementing a counter by 2 in every step. And this defines the set of reachable states. And again, we want to verify that the reachable states are all good. So we also have a description of safety property, bad state. So here, for example, the bad state is the vector where we have 1, 0, 0, 0, 0, 1. Okay? And the prominent way to verify safety properties is to find an inductive invariant. So this is a set of states, or usually we describe it as a formula. That has to satisfy 3 requirements. So it has to include all the initial states. This is initiation. It has to be disjoint from the bad states. This is the safety property. And it has to be, to satisfy consecution, it has to be inductive, which means that if we take a state that satisfies this invariant and we make a step from it, then we must end up inside this set again. Okay, so this is the inductiveness property. So if we have an inductive invariant, because of initiation and consecution, we know that it is a superset of the reachable states, and therefore, if it also satisfies safety, we know that we managed to verify safety. Okay? So back to this simple example, let's look, for example, at a candidate inductive invariant that just says that we are not the bad state. Okay, so this invariant is actually not inductive because we can take this state here, which is not bad, so it satisfies the invariant, it's not bad, but we can increment it by 2, which is the step of the system, and get to the bad state. So this is an invariant, but it's not inductive. On the other hand, if we take as our invariant the properties that said that the least significant bit is 0, basically that the number is even, then this is now inductive. Okay? So, for example, we could verify safety of this example by taking this formula. Okay? And in invariant inference, our goal is to infer these inductive invariants automatically in order to verify safety. So we have the description of the system, and we want to find the inductive invariant. And this is also what IC3 is doing. And so I'm actually very excited to talk about IC3 here because IC3 was published in VMCAI 2011. So this was also VMCAI. And immediately a year after, it already received the HVC award for its ability to show leading performance on hardware verification problems, a field that was actually quite mature and successful already. So this is a quote from what the award committee wrote, and it was also, it inspired a lot of work also in software verification, and so it was very, very successful quite immediately. And again, what we want to understand is why. What makes IC3 so effective? Right? Like to understand somehow the theory behind it. So let me describe IC3 in a very brief manner, so just like some of the principles. So what happens in IC3 is that we maintain a sequence of frames. These are just formulas, F0, F1, etc., where the frame 0 is just the initial state. And the frames have the following properties. So the frame 0 is the initial state. Each frame includes the previous frame. It's a superset of the previous frame. And also, okay, so we have this. And also each frame is a superset of the post image of the previous frame. Okay, so this is the third requirement here. And finally, all the frames are safe. None of them includes a bad state. Okay, so these are the properties of the frames. And then if at some point we construct these frames that have these properties, and if at some point we have two consecutive frames who are equivalent as formulas, or they just describe the same set of states, then we know that we have an inductive invariant, because these requirements ensure basically both. So this ensures the inductiveness, and this ensures that the frame includes the initial states, and together with 4, we get all the properties of an inductive invariant. Okay? And then the next question, so if we have this is an inductive invariant. And then the next question is, how are the frames constructed? So in a nutshell, the idea is that the frames are constructed by finding lemmas that block counterexamples. So what do I mean by that? So we have, when we talk about IC3, we have a notion of a proof obligation. This is basically a state that is bad, or that reaches a bad state in k steps, in some fixed number of steps. And whenever we see such a bad state, a proof obligation in a frame, we are trying to block it. So we are trying to learn some clause, a lemma, that blocks the bad state. And the way in which it is done, in order to maintain all the other properties of the frame, this clause has to be a superset of the post image of the previous frame, and it has to include the initial state. Okay, and usually the way in which these clauses are being learned is that we just start, we want to exclude the bad state, so we can just start by taking as a clause the negation of this bad state. So this is just a clause. For example, if this is the state, when you see that here I just slip all the bits, and this is a clause, and then we drop literals as long as we still maintain these properties. So this is, in a very simple way, how PDR learns its clauses, its lemmas that construct the frames. Okay. Yeah. Okay, and then what I'm going to focus about in this talk are two aspects of PDR. The first is the kind of SAT queries that it does. So I didn't mention that all of these checks that I described before when I described IC3 were done using SAT. So I want to talk about the SAT queries that are performed by PDR, and I'm going to talk a bit about what kind of generalization or overapproximation happens when PDR tries to learn an inductive invariant. Okay, so these are the two parts of the talk. And I'll start with the first, the SAT queries that PDR performs. And in order to tackle this question, or to look at the SAT queries, what we did was we tried to look at SAT-based invariant inference as exact concept learning form queries. So this means that we defined a model, a query-based learning model for invariant inference. And we defined different kinds of queries that can be performed, queries that can capture PDR, and queries that, as I will mention, are weaker. And we actually showed that there is an exponential complexity gap between the different query models. And this somehow tells us something about the power of the SAT queries that PDR does. Okay, we show that with the kind of queries that PDR does, we can have an exponentially faster algorithm for invariant inference. So this is what I want to talk about now. So let me just first talk a bit about exact concept learning form queries. So in exact concept learning with queries, what we have, our goal is to learn some unknown concept, and for the sake of this talk, this concept is going to be just a formula, so think of it as a formula that we want to learn. There is a learning algorithm that tries to learn this formula, And the learning algorithm can interact with an oracle or a teacher. The oracle in this scenario knows the unknown concept. And the learning algorithm can pose questions or queries to the oracle. For example, it can provide a candidate, psi1, and ask, is this the concept that I'm trying to learn? And then the oracle will answer, either say yes and we are done, or no and give a counterexample, a state that either satisfies psi1 and not phi, or the other way around. And then again, the learning algorithm can come up with another candidate, psi2, send it to the oracle will respond, and so on. These kind of queries are called equivalence queries. And there are many kinds of queries that are used in concept learning, but another common one is what is called membership queries. And in this case, the learning algorithm can take a state and ask, is this state supposed to be part of the concept that I'm trying to learn? And again, the teacher will say yes or no. So these are membership queries. And again, the process goes on until the learning algorithm finds the unknown concept. Okay, so this is what happens in exact concept learning. Okay, now let's go to SAT-based invariant inference. And like I said, we want to think of it as exact concept learning. So now, instead of an unknown concept, we have the unknown inductive invariant that we are trying to infer. Instead of the learning algorithm, we have our inference algorithm. And instead of an oracle, we have a SAT solver. Okay, that would be our teacher or our oracle. But there is a significant difference, and that is that in machine learning, it is assumed that the oracle knows the concept that we are trying to learn. And of course, the SAT solver, we don't want to assume that it knows the inductive invariant. So what we do is we assume that the oracles know the transition relation, and we actually encapsulate the transition relation such that the inference algorithm itself doesn't know the transition relation. So the only way in which the inference algorithm can access the transition relation is by posing questions to the oracle. And this is our way of somehow distilling the role of the SAT solver and the way the algorithm, the inference algorithm, relies on the SAT solver. Okay? And again, the idea is that the inference algorithm, will exchange questions and answers with the SAT solver, questions and answers about delta, the transition relation that it doesn't know, until it finds the inductive invariant. Okay, so the next question that comes to mind is what are going to be the SAT queries that the inference algorithm is going to use? And here, of course, what we want to do, we wanted to look at existing SAT-based inference algorithms and sort of capture the queries that they make. So the simplest model that we came up with was what we call the inductiveness query model. In this model, what the inference algorithm can ask the oracle, the SAT solver, is basically just inductiveness queries of this form, given some alpha I. The question is whether alpha I is inductive. If we assume alpha I and take a transition, is it guaranteed that we will end up again in alpha I? And this corresponds to a SAT query of this form. Okay, I will not get into the details, but we can ask it, pose it as a SAT question. Okay. And one thing to point out is that in this case, the counterexample would not be just states because of the nature of our query, which is whether alpha is preserved by the transitions. Then the counterexamples would also be not just state, but transitions. So transitions from sigma to sigma prime, so that sigma satisfy alpha I, but sigma prime does not. Okay? And this model actually fits and captures what happens in the ICE framework that was introduced in 2014 and had a lot of work since. In the ICE framework, this is basically what the inference algorithm does. It is supposed to come up with candidates from positive examples, negative examples, and implication constraints, which exactly correspond to this kind of counterexample to induction. So the implication constraints are pairs of states that if the first one is in the invariant, then the second one has to be in it as well. Okay? So basically, this really fits the ICE framework. And then our next question was, does this model also capture PDR, IC3? So if we look again at the sort of the pseudocode that I showed before for PDR, this looks a bit suspicious. This check here, we said that we are trying to learn clauses that include the post image of the previous frame. And this doesn't look exactly like this kind of query, checking that some property is preserved by the transition. It is more like something like that, asking whether if I start from the frame Fi and I take a step of the transition relation, will I get into a state in C? Okay, so it seems a bit different. Okay, it doesn't seem exactly like an inductiveness query. And actually, in a previous work that I had also at VMCAI a few years ago with Ari Gorfinkel and Yakir Wiesel and Sharad Malik, we really did try to describe IC3 as an implementation of ICE. We wanted to explain it in the ICE framework. And when we tried to do that, we got stuck at this point. And we said, OK, now we will extend the model a little bit. And we will also have queries of this form. But what we want to do now in this work was actually we asked the question, do we really need that? I mean, is it really, sorry, I skipped too fast. So do we really need such an extension? Okay, maybe there is a different way. So to investigate this question, what we did was first we defined another query model. We call it the whole query model, where we do have queries of this more general form. So here we ask, given a precondition alpha I, if we take a step of the transition relation, are we guaranteed to satisfy the post condition beta I? Okay, so here alpha and beta don't have to be the same. This is slightly more general. This is the whole query model. Again, counterexamples are pairs of states, basically like before. And then, now it's easy to see that this model does capture PDR. It also captures other SAT-based inference algorithms. And the question is it really more expressive? Okay, it seems like maybe it is, maybe it isn't. And then what we showed a theorem that there is actually a class of transition systems P, such that for this class there is a whole query algorithm that finds an inductive invariant in a polynomial number of queries, whereas every inductiveness query algorithm requires an exponential number of queries. So we really show that there is an exponential gap between the two models on a certain class of transition system. And I'll try to give you some idea about the proof. So first, before I continue. And actually, so it's not just that there exists a whole query algorithm. We actually showed the algorithm. We showed an algorithm, and it was actually a simple case of IC3 PDR, which really shows that the extension that we had before is, in some sense, required. Okay, now let me go over the proof in some high level, give you like the high-level idea. So first, what is the class of transition systems on which we observe this exponential gap? So these are maximal transition systems for monotone CNF invariant, short monotone CNF invariant. So monotone CNF invariant with n cubes. Let me go over what every word here means. So monotone just means that the variables, all the variables, the proposition appear positively. Okay, we don't have negation. For example, like this formula here, no negation. And maximal transition systems, so given some formula phi, a maximal transition system for phi is a transition system that looks like this. It is a transition system where from every state that satisfies phi, there is a transition to every state that satisfies phi. Okay, all these transitions here. And also from every state that doesn't satisfy phi, there is a transition to every state that doesn't satisfy phi. So we have all these transitions in this area here. And also for every state that doesn't satisfy phi, there is a transition to a state that satisfies phi. So basically, in a maximal transition system, we have all the possible transitions between states such that phi remains an inductive invariant. Okay, every transition that doesn't violate phi being an inductive invariant is there. Okay, this is why we call it maximal. Okay, so this is the class of transition systems, and now let me convince you that for this class of transition systems, PDR can find an inductive invariant. In this case, actually, phi is the only inductive invariant in a polynomial number of steps. Okay, so let's look at PDR, and let's actually look at the first frame that PDR constructs. So like we said before, the PDR constructed frames by learning lemmas that exclude bad states. And here it's enough to look at states that are reachable, that reach bad in one step because of the factor of the transition relation. And the way in which these clauses are learned, the clauses that block a bad state, we start from just the negation of the bad state. I think of the bad states as a cube, and then the negation is a clause. And again, we drop literals as long as after dropping the literal, the clause that we get is still a superset of the post image of the previous frame, which is just the initial state. Okay? So what we get when we apply this here, so note that basically in this specific case of a maximal transition system, the post image of of frame 0 of the initial state is exactly phi. Okay? So this condition basically ensures that the clause that we learn is always a superset of phi. Okay? It can never exclude states from phi. Okay? And then because we drop literals as much as possible, then we know that this clause that we learn is also minimal. Okay, so basically what we get is that the clause that we get by this generalization is exactly a prime consequence of phi. It is a minimal clause that is implied by phi. And because we look at invariants that are monotone, we know that every prime consequence is actually a clause in the invariant. So this ensures that in a polynomial in n steps, if the phi has just n clauses, then we know that in n iterations like that, we will basically find all the clauses. And every iteration just drops literals and checks. So every iteration is also just n steps. So this is why we get order of n square queries. Okay, so this is basically the proof that a PDR-like algorithm finds the inductive invariance for such transition systems in a polynomial number of queries. And just to emphasize, this is really the kind of query that we have here. It's really a whole query. Okay, we have a precondition that is different from the postcondition. Now for the lower bound, so here I will go over it much faster, but basically the idea for the lower bound states that every inductiveness query algorithm requires an exponential number of queries. So here the idea is basically that we show, I'll just skip, we just show that when we look at the inductiveness query model, having a maximal transition system doesn't really help the algorithm. Okay, taking some system with phi as an invariant, inferring an invariant for some system with phi as an invariant is just as the opposite. Inferring an invariant for a maximal transition system with phi as an invariant is just as difficult as doing so with any other transition system that has phi as an invariant. Okay, so we cannot benefit from looking at a maximal transition system. And for general systems, we have a lower bound that we also show. That is exponential, so this is how we get basically the lower bound. Okay, so altogether we get again this exponential gap between the two models. And then just as a side note, we actually, after we had this proof, we actually tried to just distill what is actually going on there, and we managed to come up with a condition on the transition relation and the invariant, somehow the relation between them, that lets us prove efficiency of inference algorithm in a slightly more general setting. And we actually showed that we can infer, if this condition holds, then we can have efficient inference of monotone CNF invariant. And actually we showed that a model-based interpolation algorithm that was already proposed before achieves this efficiency result. And we also then extended it to the ability to infer almost monotone CNF invariants and CDNF invariants. So this is just a side note, but this is, again, based on some conditions that I didn't now mention. Okay, so this was the first part. I don't know, maybe if you want to ask questions now, or maybe should we ask, wait till the end, I'm not sure. Because, okay, yeah. Yeah.
So when you are counting numbers of queries and comparing these asymptotic bounds, queries are considered equal. In practice, I guess there is a big variability in the cost of the queries. So what can we say about that? Like, did you make experiments? Did you like to see how precisely these theoretical bounds relate to what one may find in practice?
Yeah. So it's a good question. We actually didn't experiment. This is just theory. And you're right that there could be a huge difference between different kinds of queries. So, and we looked at them just all the same. But I think it's quite difficult to also characterize which queries are more difficult than others. And yeah, so we haven't done that, but I think it's interesting to try to do that. It's somehow related more to the solver side, right? Which kind of queries are harder to the solver. But what I do want to emphasize is here the kind of queries that we looked at, the inductiveness ones compared to the whole query ones. I don't see a reason why one would be more difficult than the other. I would assume that somehow the distribution is of difficulty or complexity is sort of the same, but I don't know. That's just a guess. Okay, so maybe I'll continue to the next part and then. Okay, and so this was about, until now I talked about the queries that PDR does and showed some results about that, and now I want to talk about a bit about the generalization that happens in PDR. So basically here what I'm going to show more or less is that we can think of PDR as roughly an abstract interpretation algorithm based on an abstract domain that was, that comes from the monotone theory developed by Bshouty in the context of exact concept learning. And this will tell us something about the overapproximation that happens in PDR, okay, which is what we wanted to understand. Okay, so just again to give some motivation to this investigation, let's look again at the properties of the frames that PDR constructs that I mentioned before. So before I said that PDR constructs a sequence of frames with these properties, and when we get to frames that are equivalent, then we found an inductive invariant and we are happy. And when people, in particular me, explain PDR, we always say that basically what these properties ensure is that the ith frame is an overapproximation of the states that are reachable in I steps. It's easy to see that inductively. The frame 0 is exactly the initial state, and then because of 2 and 3, we have that every frame is an overapproximation of the states that are reachable from the previous frame, so we get basically this result here, okay? But of course, our expectation is that the frames will not be just the states that are reachable in I steps. We expect somehow that there will be some overapproximation there, and this is why we hope and expect that we'll converge fast to an inductive invariant. Okay? And just to illustrate how we really don't want the frames to be exactly the reachable state, let's look again at the example of the counter that increases the value of the bit vector by 2 in every step. So here, for example, if we just think of the states that are reachable in I steps, so this is what they are. It's just in the ith step, we can reach all the vectors of where the value is at most 2i, and they are even. So if we think about that, we would need an exponential number of iterations to find all the reachable states. And we don't want that to happen. Okay? So we are really relying somehow on this huge gap between the reachable states and the frames of PDR. And what we wanted to ask is, how is this overapproximation happens, and how does it happen, and how can we actually guarantee it? So this was our question, and again, to investigate it, so what we did here, we first defined a theoretical algorithm. We call it Lambda PDR, and this was not because of the Lambda variant of COVID, even though it was at the same time. This is just because of we took the Lambda from an algorithm that Bshouty has in his paper. So Lambda PDR is a theoretical algorithm, which is somehow a simplified case of PDR, just because PDR has so many moving parts, and we wanted to try to make our investigation a bit more contained. But the important thing about Lambda PDR is that even though it's not exactly PDR, we do have a property that it gives us a lower bound on the overapproximation that also happens in PDR. So PDR overapproximates more. So if you want to understand the overapproximation and we understand it for Lambda PDR, we also learn something about PDR. And for Lambda PDR, this simplified algorithm, here we show that it is exactly, it can be understood exactly as an abstract interpretation procedure in the monotone theory. Okay? And we also showed basically that there is an exponential gap between, we showed the cases where there is an exponential gap between the number of frames that Lambda PDR takes until convergence and the number of iterations that we would need if we just did exact forward reachability, computing the reachable states exactly, or even interpolation. And again, the point is that even though this is Lambda PDR, we do have the same overapproximation also in PDR. Okay, so now let me go over this in a bit more detail. Let's start with Lambda PDR. Okay, so remember PDR, this is how we described it. We said that in PDR, the frames are constructed by conjoining some set of clauses, okay, some clauses C, where every clause excludes some bad state, a state that reaches bad in K steps. And the clauses also have these properties that ensure all the other properties. So when we look at Lambda PDR, instead of just taking some clauses that exclude some bad states, we take all of them. So in Lambda PDR, the frame, the I+1 frame, is a conjunction of all the clauses that exclude every possible state in BK in every possible way. Okay? And then this is the definition. And in Lambda PDR, the frames are computed just iteratively, one after the other. So the frame 0 is the initial state, it's the set of initial state just like before. And as long as we don't have convergence, we just compute the frames one after the other in this way. Okay, so we have this and that and that and so on. And basically, one way to think of Lambda PDR is sort of an eager version of PDR, because PDR doesn't learn all the clauses all at once. It refines its frame iteratively after it created them. And here in Lambda PDR, we just take all of them together. There will be no refinement later. And also in terms of the bad states, PDR discovers new proof obligations as it goes along. And here we just take from the start all the states that reach a bad state in K steps, and K is some parameter that we pick. So this is Lambda PDR. And again, the reason why Lambda PDR is still interesting to us is that we can show that, and it's quite easy actually to see, that for every I, the frame that PDR constructs is a superset of the frame that Lambda PDR constructs, okay, just because we took all the possible clauses that we could in the conjunction. Okay. So now, back to this outline. Now let's look at a bit about the monotone theory. Yeah.
Yeah, so starting from this Fi, are you computing the forward reachability in one step and then union it with Fi?
Do you mean in order to check this condition?
Yeah,
so
isn't this the same as forward reachability?
No. I mean, it's not this is a set of clauses. So we have this additional property that they exclude a bad state, and I will actually talk about exactly the meaning of that.
Okay.
But it's actually a very good question, because it reminds me to emphasize several things. So this is a theoretical algorithm. When we thought about it, we never suggested that anyone would implement it. But actually, as the research proceeded, we actually saw that this algorithm can also be described in a different way that is more implementable. I mean, I wouldn't tell anyone, just compute all the clauses and take the conjunction. So I will touch on that a bit later. Okay?
Yeah, thank you.
But in any case, this is something that is a bit beyond just the post-image. Yeah. Question? Yeah.
Maybe just to get a little bit more intuition on that, what is the space of all clauses here?
We are talking about, I'm not sure I understand what you mean by the space of all clauses. So our transition system has a set of variables that it is defined over. So this is just all the clauses that you can construct from these.
Basically every subset of variables?
Yeah, basically every subset of variables. For now, but again, we have these requirements that they have to satisfy. Okay. So this is, now I'll talk a bit about the monotone theory. Okay, so first monotone formula. So I actually mentioned them before as a CNF formula. So now we think about monotone formulas in DNF, doesn't really matter. But so we say that the formula psi is monotone if it has a DNF representation where all the variables appear positively. That's a definition that is not new. And we also have a semantic characterization that you're probably aware of that says that if for a monotone formula, if some state satisfies the formula and we just flip bits into being more positive, then we still get a state that satisfies the formula. This is the property of monotonicity. And then what Bshouty does in his paper, he extends this notion of monotonicity to monotonicity with respect to a state B. So psi is B monotone if it has a DNF representation where all the variables appear in polarity that is the opposite of how they appear in this state B. So let's look at an example. Suppose I take as B just a vector of zeros. Then this formula here is monotone with respect to this B, because all the variables appear in polarity opposite to 0. But this, but this formula here is not monotone with respect to this B, because we have here 0, which is exactly how it appears here. Okay, so basically you see that 0, 0, 0, 0 monotonicity is exactly monotonicity as it was defined before. But here we can take also as B a different vector, and then we get a different notion of monotonicity. So for example, the same formula from before that wasn't monotone for 0, 0, 0, 0, wasn't monotone at all, is now what happened? Oh, yeah, I flipped the example. So this was not, this was actually monotone for 0, 0, 0, 0, but now when I take here 1, this is no longer monotone, right? Because 1 appears the same rather than the opposite way. And this formula here that wasn't monotone for 0, 0, 0 is now monotone because we have this, because now everything is just the opposite of how they appear in B. Okay, so this is the notion of B monotonicity. And here as well we have a semantic characterization that basically says that the formula is B monotone if whenever we have a state that satisfies the formula, if we just flip bits to make them farther than how they appear in B, then we would still get a state that satisfies the formula. Okay, so this is now just getting farther than B rather than farther than 0 as we had in regular monotonicity. Okay, so this is about B monotone formulas, and we can extend this or define a similar notion when we have a set of states, a set of B's in mind. So given a set Bk, a set of states, we say that the formula is in the monotone span of this set Bk if it is a conjunction of clauses where every clause is monotone with respect to some Bi in the set Bk. Okay, so this is the definition of the monotone span. And actually you can see the relation that if this Bk is just a singleton, then being in the monotone span exactly means being monotone with respect to this single B. Okay, this is here. And then we can think of the monotone span of a set Bk as just a reduced product of the monotone spans of the individual state in this set. Okay, but now how does all of this relate to PDR? So what we can see is that if, as looking at the definition of B monotonicity, if as this psi here, I now just take a clause, and I say that the clause is B monotone if all the variables in the clause are in polarity opposite to B, this is exactly saying that B doesn't satisfy the clause. Okay, so for a clause, being B monotone is exactly like saying that B doesn't satisfy the clause. And this already shows us one relation to PDR. We see that this is exactly the property of the clauses that were, or part of the property of the clauses that were inferred by PDR. So we already see that all the clauses inferred by PDR or Lambda PDR, all of them are really B monotone with respect to some proof obligation. Okay, and then again, now look at this definition of a monotone span. We say that the formula is in the monotone span if it is a conjunction of clauses that are B monotone for some B, which is exactly like say conjunction of clauses that exclude some proof obligation. So you see immediately that this means that the frames both of PDR and of Lambda PDR are all just in the monotone span of the set of proof obligations Bk. Okay, so we already see this relation, and we already can now add a property to the list of properties of the frames of PDR, which is already something that is not used usually in the usual description. That all the frames are actually members of the monotone span of BK. Okay. Okay, so now what I want to show is that when I take Lambda PDR, the eager version of PDR, then it is exactly an abstract interpretation algorithm in the monotone span domain. Okay, so let me now define more precisely the monotone span abstract domain. So we have our concrete domain, which is just sets of concrete states, or I will think about them also as formulas with inclusion or implication. And for the abstract domain, we take this as the set, we take the monotone span. So just all the formulas in the monotone span of BK with the order by implication. Okay, and then we need to define our concretization and our abstraction function. So for concretization, we will just take the identity. This is the usual standard logical domain. And what about the abstraction? So given some set or formula describing concrete states, we want to map it to the least formula in the monotone span domain that includes all the states in this set S. This is what we usually want when we use abstract domains. And so what will be this alpha? So actually, if our BK here is just a singleton, then Bshouty already gives us the answer because he already defines the notion of monotonization of a set or a formula. And the monotonization is exactly what we want. It's just the least formula with respect to implication that is B monotone, which means it's in the monotone span domain, and it is implied by the formula that we want. Okay. So basically, in this case, our abstraction function will just be the monotonization that Bshouty defines and also gives an algorithm to compute and so on. And if we have a general BK, not just a singleton, then the abstraction will just take the conjunction of all the monotonizations with respect to all the states in BK. And we define this operator as the monotone hull with respect to BK. Okay, so this is the domain. And now once we have our abstract domain, we can do abstract interpretation in that domain, which means that instead of computing the reachable state just by using the concrete transformer that takes, given a set conjoined with the post image, we can just do the same using the abstract transformer or an abstract transformer, for example, the best abstract transformer, tau sharp. And okay, so we can just compute, do the computation like that. And what is the best abstract transformer in this case? So again, the usual definition, given some abstract element psi, in order to get the result of applying the best abstract transformer, we'll just take the concretization, we get this gamma of psi, we apply tau, which gives us the union of gamma of psi with the post image of gamma of psi, and then we apply the abstraction and get back here. So just as an example, suppose that after I computed the concrete transformer, I got these two states, just 0, 0, 0, 0, and 0, 0, 0, 1, 0. So now, when I apply the abstraction, and suppose that this is the set that I have now as my BK, just a singleton 1, 0, 0, 1, which is just the bed state that we had in the example. So if I apply on these two states here, the monotone hull with respect to this, just believe me, because I don't have time to get into the details of how you do the computation, but I hope you believe me that this is what you get. You just get the formula saying that the most significant bit and the least significant bit are 0, and so you already see that we had a lot of overapproximation going on, because here we started from just two states, and after applying the abstraction, we get all the states with 0 and 0 as the most and least significant bits. Okay. Okay, and now again, how does all of this relate to Lambda PDR? So what we show is that if, as my abstract element, I now take a frame of Lambda PDR, which we just claimed was a member of the monotone span domain, if I take this and I apply the best abstract transformer to this frame, then I get exactly the next frame of Lambda PDR. We get the Fi+1 in Lambda PDR. Okay? And this basically shows us that the frames of Lambda PDR are exactly clean iterations in this monotone span abstract domain. Okay, I think I do have some time, so I will try to give some intuition about what happens here in this best abstract transformer, what states are added. So basically, what happens in the best abstract transformer is that, okay, so like we saw before, what we get in the best abstract transformer is exactly applying the monotone hull with respect to BK to this set, which is just the previous frame, union with the post image of the previous frame. And now, what are these states, the yellow ones, that are added as a result of taking the monotone hull? So this is, I didn't describe exactly the monotone hull and all of that, so I just try to give you intuition. So what the states that are added are exactly state sigma here, such that for every state in BK, this sigma is obtained by taking some state in the green part, or basically all of this, the part that has to be there in the exact computation, and getting away from it, getting away from the bad state through this state. So yeah, it's a bit difficult to explain, I'm sorry. But these are the states that are added here. So states such that for every state in BK, there is some state in the area that has to be there because of actually the exact computation. And this sigma is obtained by getting away from it, going from it and getting farther from this BI here. These are the states that are added. And so far what I showed is that really Lambda PDR is an abstract interpretation algorithm in the monotone span domain. And this already makes it possible to show an exponential gap between the number of frames that Lambda PDR computes and exact forward reachability. Okay, so just going back to our example from before, the example of the counter. So we had this initial state, bad state, and our transition relation. So now we can just do the computation. So frame 0 of Lambda PDR is again just the initial state. This is as before. And now we can just compute what is going to be the first frame, F1. This is actually the example that I used before. If I take here frame 1 is applying the abstraction on the result of the complete transformer on the previous frame. So it's exactly the M hull with respect to 1001, because here I didn't mention that here is my BK, I just take the bad states, that's it. So I apply the monotone hull with respect to this on init, union with the post image of init. This is this set here. Initial state is just 0, 0, 0, 0. And after one step, I get this. So the monotone hull of this is exactly the example that I had before. This is the first frame of Lambda PDR. Okay? And if we continue doing the computation, we will see that the second frame is actually already going to be the inductive invariant. And again, the third frame is going to be the same. And we will discover convergence after computing 3 frames in Lambda PDR. And again, this is in contrast to what we described earlier that would happen if we just do exact forward reachability in this example. Okay, so we see an example where we get an exponential gap between the number of frames needed in Lambda PDR and in exact forward reachability. And we also prove that the same gap would happen here if instead of exact forward reachability, I would have used the model-based interpolation. Okay. This is just to mention that, again, the same overapproximation already exists, also exists in PDR, which is what we really care about. Okay. So this is, again, a side note. So this was what we showed that is more relevant to PDR. But actually, for Lambda PDR, we came up with some more general results. We showed that we can bound the number of frames that Lambda PDR takes for, until convergence by some parameter that is, or by some notion that is linear in the monotonization of the transition relation. And we also showed that we can bound the time that Lambda PDR takes until convergence. Here it's quadratic in that same thing. Talking about time required some new algorithm for computing monotonization. So I mentioned that Bshouty in his paper already talked about monotonizations and how to compute them, but if we try to use his algorithm, then we would require more time. So actually, basically, altogether, we did, I don't show it exactly here, but we do have now a description of Lambda PDR that makes sense to implement. And that's actually something that we are now thinking about doing, seeing what would happen if we actually implement it. Yeah. So yeah, basically that's what I wanted to describe. And so just to sum up, we saw here we basically investigated two aspects of PDR. One was the kind of SAT queries that it uses, and we showed that it uses queries that are in general richer than just inductiveness queries, and in general there is an exponential gap between what you can achieve with two kinds of queries, Hall queries and inductiveness queries, which are simpler. And in the second part, we talked really about the generalization or overapproximation that happens inside PDR, and for that purpose we defined Lambda PDR, that is exactly an abstract interpretation algorithm in a monotone span domain. And because of the property that the frames of Lambda PDR are always a subset of the frames of PDR, this also taught us something about the overapproximation that happens in PDR. And for Lambda PDR, we also managed to show some exponential gaps in the number of frames and in the time that is required. And well, yeah, I cannot say that we actually understand now the theory of PDR, but I think we do have at least some theoretical understanding of some specific ingredients of PDR. Thank you.
Yeah, thanks for the very nice talk. I am still a little bit confused about the states that you were adding from the bad states in this abstract interpretation in the span domain.
So you're asking about this slide here. Wait. So
right, exactly this one, yes.
Yeah. So
yes,
actually, if there is, well, I didn't think I would have time, but I can explain a bit, maybe more slowly, how you actually get the monotonization and then how you get the monotone hull. So basically, if you think about a formula in DNF form, and you want to compute the monotonization with respect to sum B, then you can think of every cube and just remove all the all the variables in this cube that appear in the same polarity as B. This would give you the monotonization with respect to a specific B. And this is why we think of it as a, okay, or you know what, maybe I'll look at the semantic actually in intuition. Remember we said that being B monotones means that if you get away from B, you take a bit and you flip it to be farther than B, then the state that you get should still satisfy the formula if it is B monotone. And this is what the monotonization does. It takes a formula and it includes all of these.
Okay,
yeah, just to relate it to here, the M hull is the conjunction of monotonization, and this is why I was trying to say, so you have these states that have to be there because of this part, and then when you apply the monotonization, it's like you take, from each of them, you have to, you can get away from BI, and yeah, that's how you get basically the condition.
Okay, so if I understand this from abstract interpretation perspective, is it correct to say that in fact what you are doing is applying to the green zone some kind of upper closure operator or some kind of abstraction function that is given by the bad states? So in fact you have a forward computation in like from the init, and repeatedly at each step you kind of close it up with some knowledge about where you don't want to go. Well, you don't want executions.
That is exactly that. So this is our alpha. It is just some sort of upper closure that we have a definition of. Yeah.
Thank you for the nice talk. So it's more of a philosophical question. So a PDR was developed more than 10 years ago at this point, and then you provided this very nice explanation of why it's taking I guess, much less time. Is there a way to design algorithms for inference that go from, learning theory and abstract interpretation and backwards instead of explaining them?
So
if I have a new student and I want to tell them, go look at this and come up with an algorithm based on that, what would it be like?
So actually, part of your Tom's thesis was also tackling this question. So our investigation also took us to that direction. There are many concept learning algorithms that use queries. Can we just take them and now apply them using a SAT solver? And so there are some conditions where you can do. So we showed that in general you can't. So in general, really, invariant inference is more difficult. And I don't know to say whether it's because of these counterexamples to induction that are pairs of states or what exactly, but we show that it is really a more difficult problem. But under certain conditions, this is the condition that I mentioned, we call it a fence condition, some condition about the relation between the transition relation and the invariant that you are trying to infer. Under certain conditions, you can actually implement queries, certain queries that are used in concept learning, and then just get an invariant inference algorithm. So there are some cases that we identified where you can do that, and this is how we show that you can achieve efficient inference for almost monotone CNF invariants, again, under this condition. And for CDNF invariant, again, under this. Actually, CDNF, we didn't actually get it as an implementation of a concept learning algorithm. For that, we needed to do something a bit different, but it used similar ideas. So the best that I can tell you is this condition that we managed to find relating the inductive invariant and the transition relation, but maybe there are other conditions. I think it's very interesting because there is a lot of literature in exact concept learning, and we somehow do the same thing, right? We are trying to infer an unknown concept, but yeah, that's all that we could do.
Thought I have one. So I found really interesting the example system that you have separating the exponential complexity of the one algorithm versus the other. I wonder, from theoretical perspective, it's pretty interesting. Do you have any evidence that this kind of example could arise in practice and account for some differences in efficiency?
So maximal systems, I wouldn't expect them to occur. They are really very artificial, but the other condition that we came up with, which somehow generalizes this could, but it's quite difficult to, so we couldn't do a real analysis. We were considering, but we didn't manage to really analyze existing examples and check whether they really do or do not satisfy this condition. So I don't have a good answer.
Or maybe a simpler question, like, is there in the literature a noticeable performance difference between the two algorithms that this could account for?
Okay, so you're asking, for example, take cases where interpolation works worse than IC3, and could I explain it in this way? Yeah, I don't have a good answer, but it's actually an interesting question to investigate.